Now, if you take a quantum field theory and have a particular source of the thing, it turns out that it emits individual quanta, and a quanta just travel. Of course, I tend to act like a teacher all the time, but it's already a mystery that a photon is emitted from the atom, because a photon is so much larger than the atom, and yet we are told that it emits, and also from the electronic shell, which is much bigger than the nucleus. And what happens for this thing? Big photon comes and then somehow pounces on one of the electrons and pushes it out. But when you consider that light is a quantum mechanical object, photon, you can then try to apply the methods of quantum field theory. And the simplest of this one is the case of a local charge current distribution emitting a photon. The photon is emitted as a whole, and if there is a lot of light, then it may happen that other photons are emitted. But these are all corresponding to independent photons. So, when do photons do this thing? The answer is that all the time. If you take a point source, classical source, and couple it with a quantum field, then the corresponding state that is created is a coherent photon. And if you have two parts of the same thing, then they would be completely in phase. This was known to Schrödinger, and in the book Mathematical Foundations of Quantum Field Theory by Friedrich, this is solved as a prime example of the success of quantum field theory, namely that you can describe the emission of light by coupling a classical source to the electromagnetic field. These have been rediscovered by people, and the rediscovery, the notion was that if you consider the electromagnetic field and its coherence, you find that the coherence survives as long as the photon does not interact with anything. But you don't always want to talk about classical sources emitting single photons. You want to talk about what happens when many photons are around. Yeah, 5 minutes. And the notion of coherence can be made very, very clear by looking at what is called the two-point function. Instead of considering the wave as a function of a point, you consider 2 points in the field and then say, are they coherent with each other or not? This is called mutual coherence, and it can be shown that this behaves very much like any other wave. It spreads out locally together, then they are coherent, but when you separate out, there could be a spreading of the thing. But ultimately there is a question. It's a quantum effect, and therefore you must talk about it in quantum language. And when you do it in quantum language, what you find is that the photon wave function, or the intensity as we normally call it, must be not always completely positive. And I had looked at this question. You know, Rochester was a hotbed of optics. There was Emil Wolf, who knew all about classical optics, and then Leonard Mandel, who is now no more, who not only did theory but also experiment, and therefore he knew what was happening. Given this particular system, there was the question of what modifications are introduced into this one by considering the notion of quantum coherence. Quantum coherence means coherence in the wave function or the description of one photon, and then of course therefore many photons. I had occasion to look at this thing, and I wrote a short paper. Again, this was much shorter than the previous papers. It was about 1.5 pages. And I showed that it is very simple to find out the thing. There is a certain distribution, classical distribution for quantum systems called the Wigner-Moyal representation. By a slight adjustment of that thing, you get another distribution, which is called Husimi-Kano distribution. And if you take that distribution, then it is the ideal tool for talking about coherence. And if you did that, you could find out what it is. It turns out, while this is all very nice, it does have a big problem, namely that it disagrees with our intuition that this distribution function must be completely positive. In this case, it was not completely positive, and in fact, classical things are distinguished from quantum things by saying that the coherence amplitude must not be positive definite but contain negative elements. I was roundly attacked by my friend from Harvard who said that Sudarshan says this is negative, but everybody knows that it should be positive, so we should disregard what he did. He not only wrote once, but wrote it many, many times, and therefore many people were convinced that he is the discoverer of quantum coherence. Nevertheless, there is some doubt in some people's mind, and mainly they look for the quantum statement, and you don't find it. You find only that you can define such states, but not express every field in terms of this one. So we find that there are possibilities of anti-coincidences or anti-correlation of the light distribution at two different points. And also, if you consider the counting statistics, when the when the photons are considered as random events, then it turns out that the distribution of counts within any interval of time is distributed according to the Poisson law. N, for n being integer, for every integer you can write down the thing. If you have classical stochastic processes, which is not pure but contains mixture of many things, only thing that can happen is that the counting distribution contains even more variance than the classical case. In other words, these are sub-Poissonian statistics, and therefore if you are careful enough to get the light source to manifest itself in terms of quantum coherence, you should find that the Poisson law is no longer valid, that there would be a sub-Poissonian distribution. Both these unusual predictions are verified in some experiments that Mandel did, along with Kimball. Kimball is a good friend of mine. I should not mispronounce his name. For two reasons. One, he is a good friend and is a very good physicist, and also he is much taller than me. Whenever I talk to him, I look up. So it is not a good idea to say his name in a bad fashion. And they verified that you have both sub-Poissonian statistics and also a situation in which the intensity seems not to be positive, have correlations, anti-correlations between the fields at two different points, which finally established all the necessary things about this. I have many more things to talk about, but the chairman has kindly indicated that I should get off here. And a few years ago, some of my friends said that the reason why your things are not fully appreciated is because of the fact that you write it in different places and short papers. So they said we should have an international conference in which your work is highlighted. So they did highlight it. We had it for my 75th birthday. I didn't feel any different after the meeting, but eventually the proceedings came out, and when I look at it, I feel very pleased, because all the people who are contributing to this are people who are my friends, and they don't want to steal anything from me, and they have exposed it very, very nicely. I will leave a copy of the proceedings in the library for those people who would like to look at it. And now, before anything else is done to me, I better leave here. Thank you.